Right, okay, so this presentation is going to explain everything you need to know about how Bitcoin keys and addresses work. So you might have heard of things like private keys, public keys, and addresses. In this presentation, I'm going to describe or explain where they come from and how they work. So a quick outline of what's going to be in this presentation. I'm going to start with the basics, where do keys come from and how do they work. So just a very basic overview of how they all work. And then from there, I'll cover how each key is made. So you have a private key, and then from that you have a public key. And these are the two main keys that you use in Bitcoin. It's kind of like a password and an account number. And from there, you have what's called digital signatures. And these are used to prove that you own a public key. So it's like for signing transactions. So I'll explain how those work. And then after that, I'll cover how addresses work. Like, addresses are basically just like a pretty version or a more user-friendly version of a public key. So I'll explain how they work and how they all connect together. And then at the end of that, I'll just go through some code and some examples to show you how you can generate your own private key, public key, and address. So yeah, at the end of this, it's all mostly presentation stuff in this presentation, not too much code at the end. It might be a little bit heavy on the explanations when it comes to digital signatures, but as long as you just get a feel for it of how it works, that'll be fine. So I'll get started. Oh, and also this is why Bitcoin and other currencies are called cryptocurrencies, because this private key and public key stuff is called uses cryptography, and so that's why we call them cryptocurrencies. It's like the backbone of the transaction system or the ownership of Bitcoins. So just to get up to speed on where we left off last time, from my last presentations, this is the Bitcoin network, like so, and the Bitcoin network is just a bunch of computers all connected together and sharing this file called the blockchain. And when you want to make a Bitcoin transaction, like so, you want to send someone some Bitcoins, you make a transaction like this, which is just a line of data that describes the movement of this Bitcoin from this person to this person. And then when you want that transaction to be added to the blockchain, you will insert the transaction into a node on the network. They will store it in their memory pool quickly, and then they'll pass on that transaction to the nodes they are connected to, and so on until the transaction is in the memory pool of each node on the network. After that, all of these nodes then will try and compete to try and add the transactions in their memory pools onto the blockchain. And this process is called mining. So let's say this person or this miner was able to add the transactions from their memory pool onto the blockchain. So there's a block of transactions being added. Once they've done that, they will pass on that block to the nodes they're connected to, add it to their blockchains, and so on until everyone's copy of the blockchain is updated with the latest block of transactions. And then this person can look at the blockchain and see that the ownership has changed from this person to this person. So in the last presentation, I covered what these transactions look like on the inside. So you can think of a transaction like this. So the blockchain is full of all transaction data, but if you were to sort of split it open and look inside, it's basically like looking at lots of different batches of Bitcoins, all different sizes. So when you make a transaction, all you do is you go into the blockchain and you select a specific batch of Bitcoins. So let's say this one is a batch of 10, and then from there you will take that batch of Bitcoins and create a new batch from it. So send in a batch to just creating a new batch from an old batch. So what you do then, you'll send that batch of Bitcoins into the this transaction that takes a batch of Bitcoins, creates a new one into the network, and then that will again go into a memory pool, the transaction, and then finally into the blockchain. And then when you look at the blockchain, then this new batch will appear here in this new block, and this old batch that we used up is grayed out. It's grayed out because it's spent. I've been calling these batches, but they're actually called outputs. And when you use an output, when you're spending one in the transaction, it's referred to as an input. So you can think of the blockchain as full of outputs that just basically get selected and new outputs are created from them. So that's all well and good, but how do you own these batches of Bitcoins? Well, every single batch of Bitcoins has a lock on them, and every person who wants to use Bitcoin has their own set of keys. You have a private key, which is like your password, and you have a public key, which is like your account number. So when you want to make a transaction, if this batch of Bitcoins belongs to you, then you can use your private key to unlock them. And then from there, you can create a new batch. And if you want to send Bitcoins to this person, they will give you their public key. And using that public key, you can create a lock on this output, this batch of Bitcoins, that is locked to this person's public key because they gave it to us, like so. And then if they want to send this batch of Bitcoins, of 10 Bitcoins, onto someone else, they will use their private key to unlock it and send them on. And so that's a typical transaction. That's how they're owned, through the use of these keys, the private key and the public key, which is the equivalent of having an account number and a password. So again, like I said, once you've constructed this transaction, changing the ownership of a batch of Bitcoins you own and creating a new batch that are locked to a different person, you'll send that transaction into the network, and eventually that transaction will get mined onto the blockchain, and the batches of Bitcoins will be updated like so. So this one has been spent, it's been grayed out, it can't be spent again, and a new batch arrives in a new block that belongs to someone else. So if you want to use Bitcoin, all you need to do is just have your own set of keys. So again, if you just want to receive Bitcoins from other people, you just need to have your own set of keys to be able to use Bitcoin. So where did these keys come from? Well, I can tell you where they don't come from. There's not one single person in charge of Bitcoin that has a book full or a computer full of sets of keys that you can ask to give you a private key and a public key. There's no one you need to ask to give you a public key. So this is what a bank might be like. So if you go to a bank, you have to ask someone for your own account number and password to use their services to send money and receive money. But in Bitcoin, we don't have a central authority because Bitcoin is decentralized and no single person is in control of who can use it. So that's not how Bitcoin works. So if there's no person in control of sets of keys or account numbers that you can ask to give you, where do they come from? Well, the answer is we just generate our own private key and public key. So there's no person that we ask or we have to, get these keys from. We literally just create them ourselves. So anyone basically can use Bitcoin because we create our own account numbers and passwords. So that's the intro done. Hopefully all that makes sense. I'll move on now to the basics of creating, generating and using these keys. So how do you generate your own set of keys to be able to send, receive and send Bitcoins? Well, first of all, you start with a private key, and the simplest way, the only way to generate your own private key to start out with is just to generate a random number. So like so, you'll just generate a random number. This is obviously a very small number. Bitcoin private keys are much bigger numbers, but this is just to show you. And then from there, you need your public key. So if the private key is your password, the public key is like your account number. But obviously, because there's no one giving out these sets of keys, when we generate our public key, we want to have a connection between our private key and our public key, so that when we use them, so that we can use our private key to unlock Bitcoins because they're connected. So how do you create a connection between a public key and a private key? Well, what you do is you just use some mathematics to derive your public key from your private key. So you basically take your private key, put it through some mathematical functions, And then that will give you a public key. And so this public key is connected to your private key through mathematics. That's where the connection is. So again, when you generate a set of keys to be used in Bitcoin, you start with your private key, it's just a random number, and then from that you create your public key or your account number, which is just a mathematically connected number that's connected to your private key. And that is how you generate your own set of keys so that you can receive Bitcoins from other people and then send them on to other people also. So anyone can do this. Anyone can generate their own set of keys to be used in Bitcoin. So that's the basics done. Now I'm going to start with this private key, because generating your own set of keys, it all starts with the private key. So move this across. There we go. Like I said, your private key is just generating a random number. And this random number can be between anywhere from 1 to this number. Now this is a very, very large number. But as long as you generate a number between 1 and this value, it's a valid private key, or your valid starting point, your valid password to use Bitcoin. This is often referred to as a 256-bit number. This just describes the size of it, how big the number is, and that comes from basically computers. They store data. You have kilobytes and bytes and megabytes. Well, a bit is the smallest unit of data that a computer can hold, and all that is a 0 or 1. And so all the data on your computer is ultimately stored in a sequence of zeros and ones. So same thing for numbers. When you want to store numbers on a computer, they are also stored in zeros and ones. So if you want to store numbers, starting out with 0, you can store that quite easily in bits by using the number 0. The number 1, similar thing, you can just use the bit 1. But then for the number 2, you've run out of characters that you can store this data in, so you just add another bit in. So in binary, or in a sequence of bits, the number 2 is stored as a 1 and then a 0. And then again 3, 1, 1, but then you've run out of options again, so you need another bit to store a bigger number, like so. So this goes on and on. So the bigger the number becomes, the more bits you need to be able to represent it or store it on a computer. So if you carried on doing this, and you had 256 bits lined up together, and you put ones in all of them, then that would be able to store this number here. So that's why it's called a 256-bit number. It's basically what a computer, the largest number a computer can hold in 256 bits worth of data. And that's also the same as saying 2 to the power of 256, because we have two options for each block here, and that can either be a 0 or 1. And if you do that 256 times, so to the power of 256, that gives you this number here, 2 to the power of 256, which is a very big number. So then the question now is, what if someone generates the same private key as me? This obviously seems like a bit of a crude mechanism for generating your own private password to be able to use Bitcoin. Well, the answer is that this number is so large that nobody is going to generate the same private key as you. To illustrate that, let's say this is the known visible universe. This number here, this is the number of atoms in this known visible universe. So as you can see, which is 10 to the power of 78, as you can see, this 256-bit number here is not too far off from the number of atoms in the universe. So you just have to trust me when I say that, because this number is so large. I mean, it doesn't particularly look large here because I can display it on a screen, but this is unbelievably large. And the fact that it's so large means that two different people are not going to generate the same number. And that's just how big it is. and that's how secure it is. And this has been working fine in Bitcoin, no problems. There's been no known case of anyone generating the same private key, or not that I know of anyway. And if there was, it would be big news. But like I said, it's a very big number. So private key, you just generate a number up to between 1 and this value here. Just generate it, and that'll give you your private key. Does that make sense so far? Okay. Right, so private key, just a random number we've just generated. From that, we can now get our public key. So, like I said, with our public key, it needs to be connected to our private key somehow, because we need our account number to be connected to our password. So the way we do that is we use some mathematics, and there's a particular type of mathematics we use, and that mathematics uses this thing here, which is called an elliptic curve. You have lots of different elliptic curves. This is just an illustration of one, but the particular one used in Bitcoin is called SECP 256K1. So like I said, there are lots of different elliptic curves, but this is the particular one, the particular shape that Bitcoin uses. And so to get your public key from this private key, you have to do what's called elliptic curve multiplication. The reason why we are using this elliptic curve will come apparent later on, so just bear with me now while I show you how this elliptic curve multiplication works. So with the SECP 256K1, it comes with a starting point, and to do multiplication, this is going to be a simplified explanation, but it's basically this is called G, by the way, the starting point or the generator point. But for multiplication, it's basically draw a tangent on the curve, a tangent at the point on the curve. So we'll start at this generator point here, and one of the properties of this elliptic curve is that if you draw a tangent on it, then it's always going to intersect the curve at one other point. And that's just one of the properties of this particular type of curve, and that's why we use it. So after you've done that, when it intersects this point, you take that point, called the intersect, and then you just invert it and take the opposite point on the curve from this point here, from the intersect. And when you take this point here is like doing one round of multiplication. So if this was 1G, this would be 2G. And then again, if you want to do another round of multiplication, draw another tangent, and it will intersect another point on the curve, and that will give you, then you take the inverse of that, and that will give you, another point on the curve, and that is a second round of multiplication. This is a bit simplified, but this is basically how it works. So again, when you want to multiply again, you just take another tangent, get another point on the curve, and so on and so on. So basically, when you're doing elliptic curve multiplication, you're drawing all these tangents and taking the inverse points, but ultimately what's happening, you are bouncing around this curve in a particular way, like this. So what you do then, you'll bounce around the curve this many times. So you'll bounce around the curve private key times. So obviously I've done 10 there, but you'll keep doing this until you've done it private key times. Once you've done that, there we are. Once you've done that, you'll end up with a point on the curve, and this point on the curve is the public key. So there are many, many, many points on this curve. Basically about as many points on this curve as there are private keys. So once you've got that public, so basically, like I said, this final resting point on the curve after bouncing around it this many times gives you a public key. And to be precise, your public key is just the X and Y coordinates of this point. So there we are, that's the X and that's the Y. Put them together like this, and that is your public key. One of the reasons why we use this elliptic curve is because one of the properties of it is this multiplication is what's called a trapdoor function, which means that you can easily do private key multiplication. Well, do multiplication using private key, and you can bounce on the curve. But going backwards, taking this point on the curve and figuring out what the private key was from that is very difficult. Well, it hasn't been solved yet. No one knows how to take a public key or a point on the curve and figure out what the private key was, the number we multiplied the generator point by. It's a bit hard to explain why. I think this elliptic curve deserves a video of its own, but all I can say is that you're doing a lot of modulus mathematics, and so a lot of information gets thrown away whilst you're doing this multiplication stuff. So it's just very difficult to go backwards, and that's why we rely on this elliptic curve to basically protect our public keys and private keys. And this, if you want to find out more about why you can't go backwards, it's called the elliptic curve discrete logarithm problem. But there we go. So we've started with a random number, we've done some elliptic curve mathematics, and we've got a point on the curve, and that is our public key. So this is the mathematical connection. Through this elliptic curve, we have a mathematical connection from our private key to our public key.
Is G always the same?
Yes.
Or
yes. So you have different curves. This one's called SECP. This one, and so that comes with a particular G generator point.
Oh, got it. So it's not really a Bitcoin thing. It's more of the G.
Yeah, it's more like a
G
cryptography thing.
Yeah,
Yeah. So you can have different curves, but Bitcoin uses this particular curve and these particular parameters. So there we are. So that's creating our public key. So now we've just generated our private key and our public key. We can start using Bitcoin. So if we want some people to send us Bitcoins, we just give them our public key, like so. So they've got a copy of our public key, and then they can unlock any batches of Bitcoins that they own, create a new batch and put a lock on it, and lock this batch of Bitcoins to our public key. So when we want to send Bitcoins, then the ones we've received that have been locked to our public key that we've given away, we just we create the transaction first, we want to send them, and then we use our private key to unlock this lock, or basically prove that we created this public key, or that we have the mathematical connection to this public key, and no one else should have it. So how do we prove that we created this public key? How can we show that we have the private key that this public key was created from? Well, a bad way to do it would be or one way of doing it that would be bad, would be just to put your private key into the transaction you've created. So what that means is anyone could look at this private key and public key and say, okay, this person obviously has this private key because they've given it to us, and they can see the mathematical connection for themselves. They can do the elliptic curve multiplication and get the same public key, and that proves that we created this public key. But the problem is, when this transaction goes out into the Bitcoin network, it's going to be in all of these nodes, and so anyone can see this publicly exposed private key. And if they can see it, then what they can do, they can take that private key, and if there are any other Bitcoins locked to the same public key as this one, they can just copy our private key and basically take all of the Bitcoins or outputs that have been locked to this public key before. So the last thing we want to do is give away this private key. So that won't work. So what can we do instead? We need to put something here in this transaction that proves that we created this public key. And we need to put something here that only we can create, that no one else can put here to unlock this batch of Bitcoins. So what do? Well, we use our private key again, but instead of putting our actual private key into this transaction data, you create what's called a signature. Now, these signatures are very handy because they are created from the private key, and they can actually still prove that we created this public key. But the good thing is, well, one, it doesn't give away our private key, and also they only work for the transaction that we're signing. So if someone else sees this signature and we've got other bitcoins locked to this public key, they can't just look at this signature, take it and put it into this transaction or a transaction they create, because that won't work, because this signature only works for the one transaction that we are creating. So you could think of a signature as a sort of special one-time private key that we use to unlock batches of bitcoins. Does that make sense? I'll cover the details in a moment, but as long as that makes some sense, that's just the very basics of signatures. So we've got a private key, got a public key, but now we need to figure out how to create digital signatures. How can we create this thing here that will unlock this transaction or this batch of bitcoins for this transaction without giving away our private key? So that's what I'm going to cover now. So a signature, we need to create a signature. I'm going to run through this a little quickly. I'm going to cover the absolute basics. Don't worry if it doesn't make complete sense on the first attempt. Just as long as you get the gist of it, that's fine. It involves some mathematics. So let's move this all out of the way. There we are, just move everything out of the way. Put that down here. Now we need to create a signature. There's 2 steps to creating a signature, and it involves the use of this elliptic curve again. No surprises, that's why we use the elliptic curve in the first place, because we can use it again to create signatures. So the first part of this 2-step process for creating a signature is you need a random part. So what you do is you start out by generating a very big random number and then doing some elliptic curve multiplication again, just like we did earlier, and that will give you a random point on the curve. So this is very similar to what we did earlier. We just took a private key and created a public key. This is the exact same thing, but we're just using a random number that's going to be used for this one-time signature for this transaction. And so this random point on the curve that we generate is called R. Or more specifically, we just need the X value for it. Secondly, using that random point, or the X value, which is just a number, we multiply that by our private key, which again is just a number. And then we add in what's called a message, the thing we want to sign. So the thing we want to create a signature for is this transaction here. So we basically put that transaction into here as the message, and this is all just a bunch of data. But just we don't put the actual full data in there. What we do, we just hash it and put the hash of the data in there. But basically, we've got the random part, this X value. We multiply that with the private key, and then we just add in the fingerprint for the transaction we want to sign. And then we just divide all that then by R again. So the key thing here really is that we've got a random point on the curve, and we've got this special number here that contains a mix of our private key and the transaction we want the signature to work for. And this is called S. So as you can see, the private key and the transaction data is in there, but it's all jumbled up. So if anyone could look at this S value, but they won't be able to see what our actual private key is because we've used this R and whatnot to scramble it up a little bit, but it's all in there. So the signature then is just these 2 parts. So you put the R in there and you put the S value in there. So the R is just a random point in the curve. The S is a special number that contains our private key and the transaction data we want to sign. And that is our signature. Signature is just an R and an S value. So move that up there. That's the first part done. Go on. Yeah, go on.
Can we just go back to the previous slide? If you can quickly go through this again, Craig, it will be awesome. So the first part you mentioned was we take the elliptical curve. We have the same G in this case.
Yeah.
we generate a random number. Is
Yes.
that right?
So this is just a random number. Yeah. You just generate. Yeah. Go on.
Yeah, and we multiply that random number with g. So we keep hopping around the curve until we get to a
Yes.
point.
Yes.
Right. Okay. After that, and at this point, like our public or private key has not come into the picture. It's just
Yes.
this
Yes.
random point. Okay. Yeah. Let's go to number 2 now. Okay. So we take x from
Yeah.
R. We multiply it with our private key. So we'll again be hopping around this curve.
No, sorry. This is not elliptic curve multiplication. This is just pure normal mathematics. So if you remember, our private key is just a number, and this x value is also just a number. So we just do normal mathematics. Yeah.
Normal mathematics. Okay. It's not elliptical curve multiplication. No. Okay. Okay. And the message is basically our what was that again? Is it the transaction data?
Yeah, just the transaction data. So by putting the transaction data into here, that means that this signature will only work for this particular transaction. And obviously the private key is here just to prove that we own this public key.
Right. And from the previous video, this is the transaction data without the signature. Right?
Yes, that's correct. So you take all the so you take all the signatures out, and then you hash the data and put it into here. Yes. Good memory. Yeah.
Okay. And we divide that by R.
So these R values serve to help to scramble up this, our private key, basically.
Right.
Okay, so there we are. So that is a signature created. It has two parts: random point on the curve, and a special number derived from using our private key. Now, we'll see why this works now. Why did we create these two things for the signature? Well, when we send this transaction data, or this whole transaction, into the Bitcoin network, every single node on the network is going to verify that this is a valid transaction. So they're going to take this signature, and they want to be able to say, okay, this signature could only have been created by the person who owns the private key that this public key was created from. So they need to verify that to make sure that this signature works or was created from this particular private key. So how can they do that? They haven't got the private key. All they've got is these two values, the R and the S value. But the S value has been created from this private key. So how do they do that? Well, first of all, they take this R value that they've given them, and this is they just start with that. And again, this is a two-step process for them as well. First of all, they do some normal mathematics. They just multiply the hash of the transaction data with that R value, and that will give them just a very big number. And so what they do with that very big number on this first step, after multiplying these two values together, they'll start at this generator point, and they'll do elliptic curve multiplication using this big number they've multiplied, starting at G, and they'll bounce around it, and that will give them this first point on the curve. Second of all, they'll do some more normal multiplication again. They'll just do S times R, so they'll just take this S value, multiply it by this R value, and then starting this time at the public key, they will bounce around the curve this many times. So they'll bounce around the curve this many times, and that will give them a second point on the curve. And now, the magic part here is if all three of these points on the curve line up, then that means that this signature is valid. So with elliptic curves, if you draw a line through 2 points on the curve, just like a tangent will always intersect one other point on the curve, if you draw a line through 2 points on the curve, that will always intersect one other point on the curve as well. So by generating these 2 points on the curve using these two values that we have been given, along with the public key and the transaction data, we can generate these 2 points on the curve, and if they all line up, then the signature is valid. So what that means is that if someone tampers with the transaction data, so we give them this transaction data and the signature, and then they try and send the bitcoins to their address, they tamper with the transaction data, that means that this value will be different. And so when they generate the first point, that'll be different, and they won't all line up. So the signature won't work then. So that protects this transaction data from being altered. Similarly, if someone tries to create a signature to spend our bitcoins using a private key of their own, not the one that we created the public key from, so a different private key altogether, that means that when they generate this S value, that'll be completely different. And if that S value is different, then this number here is going to be different. So when we do the elliptic curve multiplication, starting from the public key, this point is going to be different again, and the points won't line up. So this is a very basic overview of how digital signatures work. And if all you understand is that private keys and public keys are connected through elliptic curves, and the reason we use elliptic curves is because we can create these signatures and other people can verify them doing some elliptic curve mathematics. And these are the special properties of elliptic curves. So again, just to summarize, like I said, you just take a private key, you do elliptic curve mathematics, multiplication to get the public key, and then you give that public key to other people, and they'll put that, or they'll lock up a batch of bitcoins to that public key. But then from there, we need to, when we want to send them on to other people, we need to prove that we are the creators of this public key. So what we do, we take our private key, create a signature, which again involves some elliptic curve mathematics, and then we give them that signature, and then they can do some verification to verify that we created this signature from the correct private key. And they do that by taking this public key and the signature and also the data, and they generate 3 points on the curve, and if they line up, then that signature works. And again, if someone doesn't use the right private key, they won't line up, or if someone alters with the transaction data, they won't line up either again. So it's a bit magic, this whole process, but ultimately it's all mathematics. And if all you take away from this few slides is just that this elliptic curve mathematics is very good for cryptography and for creating account numbers and passwords, and then being able to prove that you own the account number without ever giving the password away, which is very clever. So this is called elliptic curve cryptography, and it's very, very useful, and without it we would not be able to send and receive bitcoins safely without having a person in control of all the sets of keys. So this means through this elliptic curve cryptography we can generate our own account numbers and passwords to be able to send and receive bitcoins, which is very, very handy. And again, like I said at the start of this video, crypto, this is why Bitcoin and other currencies like it are called cryptocurrencies, because they use cryptography as the backbone for the ownership of these batches of bitcoins. So let me just move all this back to here. So that is private key, public key, and the signatures done. So this is the basics of sending, receiving bitcoins in Bitcoin. Just these set of keys and creating digital signatures to prove that you own the public part of them. So from there, you've probably heard of addresses. What are addresses? Well, addresses are just basically prettier versions of the public key, more user-friendly versions of the public key. So originally, or you can still do this in Bitcoin, you can just generate a private key and a public key for yourself, give that public key to other people, they will lock up bitcoins for you, to that public key, and then you can use that private key to create a signature and send them on. But This all works well and is fine. If someone looks at this public key, they can't figure out, like I said before, what the private key is, because you can't go backwards through this elliptic curve multiplication. You can go this way, but you can't go that way. But what it does mean is that this is not known to have been solved at this moment in time, and it doesn't look like anyone's going to find a solution for going backwards through the elliptic curve. But it does mean that if it was ever broken, then your public keys or your bitcoins can be stolen. I mean, there's no one can see this happening for the foreseeable future, but it does mean that this public key is like a sitting duck waiting to be broken if this elliptic curve can be broken. So in Bitcoin, we like to use a bit more security. How can we not have to just rely on this elliptic curve discrete logarithm problem to protect our bitcoins? So the solution to that is, what we do is we just hash this public key twice through two different hashing functions. The first one is SHA-256, which is the one you should be familiar with from mining, and then also a second one is used called RIPEMD-160. So what this does is like double hashing through two different hashing functions the public key. And then what you do then, you'll give that hashed version of the public key to other people instead of the standard public key. So this is like a scrambled version of this public key. You give that to other people, and then they'll actually put these in the locks. So what that means is, whilst this hash version of the public key is in the lock, if someone wants to go all the way back to get to your private key, instead of just going back from the public key and trying to go backwards through the elliptic curve, which you can't do, but that's the only hurdle to jump over. If you want to figure out your private key from this hashed version of the public key, you have to go basically you have to break the RIPEMD hash function, which no one has done. Then you also have to be able to go backwards through the SHA-256 hash function, which no one has done. And after doing that, that'll give you the private public key. Then using that, you have to go back and break this elliptic curve, which no one has done either. So this hashed version is a very, very secure version of the public key. So the reason we create this is because all of these batches of bitcoins, they're all going to contain a public key. So this is just a very safe version of the public key to give away, because it's hard to get back to the private key. So if this is going to be a sitting duck, let's make it very safe. So there we are, that's the public key. What do we call this? There isn't really a particularly fancy name for it. We just call it the hash 160 of the public key. So we just hash because we're using hash functions, and the last one we use is the RIPEMD-160. So it's commonly shortened to hash 160 public key. So there we go. So that's all well and good. We've hashed this, but the problem is now, before we would have just put the public key in here and then created a signature and put that in there. But after we're hashing this public key, there's no mathematical connection, from this hashed version to the private key. So we can't just put a signature in here. So when we want to send bitcoins, what do we do now? What do we put in this space here, this unlocking code? Well, we still put the signature in here, but along with the signature, we actually put in the public key also. So what that means is, so this lock now has adjusted a little bit to say, give me a public key and a signature. And what it'll do then is, the first thing it'll do is it will check that the public key that you've put here hashes to this hashed version of it, through this two, and anyone can do that through these two hash functions. And after doing that, it'll do what it did before, just check that the signature works. So whereas before we had the public key in here and it was like a one-step process of comparing the signature to the public key, this is now a two-step process where it first compares the public key to the hash version that you've given away, and if that checks out, they will check the signature against the public key. So basically it just adds another step. Yeah, go on.
So in that sense, we do have public keys which are for the hash 160s. That is open information, right?
Yes.
If I okay,
Um,
okay. So
Another
yeah,
question probably that you'd be thinking now is, okay, well, what's the point in hashing this and giving this away if eventually we're going to be giving the public key away anyway?
yeah. Blocks are smaller, I'm guessing, but I don't know.
Well, the thinking is that this public key is only given away at the last moment. So
Okay,
say it took some time to be able to, brute force and get backwards through this elliptic curve, that if it was broken in some way, well, if it was, first of all, if it's completely broken, then your bitcoins are safe. So if you just don't spend them, then they're still, no one else can take them, but then that's obviously not very good. But this, well, the thinking is that this is like only given away at the last moment, and if it's given away at the last moment, then hopefully other people won't have the time to be able to work backwards quick enough to be able to steal your bitcoins. But on the plus side,
got it.
well, I think it's better than nothing, really. So this is why we use this hashed version. So this hashed version, it doesn't give anyone any incentive to try and work backwards through this elliptic curve, because they have to get
Right,
through these first. So it's basically gone.
right. So my thought is that let's say we have say 10 bitcoins behind this public key.
Yes.
Yeah, and we spend say 1 bitcoin out of those
Yeah.
10 bitcoins. So at this point of time, an attacker has the public key for the hash 160.
Yes. But what you would,
And at that
yeah,
point,
what you
yeah,
would do, say you want to
tell.
send, say there's 10 bitcoins here, and we want to send one
Uh-huh.
bitcoin to someone else, and then we want to
Right,
keep the change for ourselves. What is
right.
recommended is that you create a new address. So that's why everyone says
Okay.
don't reuse the same address. That's because when you send the change to yourself, if you use a different address, then even though you're giving away this public key, it's effectively useless, because all of the bitcoins that were locked to this public key are now been spent and moved on. So that's why everyone says to
That's
not to use different address, or to use different addresses every time for your change.
right, right. Yeah, then the last minute logic makes sense in that case. Because if it's a new address, then again, we don't know the public key for that
Exactly.
hash
Yeah.
160 for the
Yeah.
new.
Exactly.
Yeah, awesome.
Right. So I'm glad that made sense. But so obviously now you can still use if you go back, you can still use this method of just putting the public key in here, and you can still create locks that do this, and that is perfectly fine. But when people, all of the wallets these days, they all built to use this hash version of the public key because it's more secure. But you can still use this, put a public key in here and then just use one signature. That's how a lot of early transactions in the blockchain, if you check them out, they use a very simple public key and one signature. But all the transactions now, well, the more recent ones, they use the hashed version inside this lock, and then they put the public key and signature in the unlocking code afterwards. So by here I've just done a wordy description of how these locks work. The next video I'll do will be actually looking inside these locks to look at the code to see how they actually work. So this is the locking code, the lock, and this is the unlocking code here. So okay, finally, like I said, what is an address? I had to go through this just to show you where an address comes from. So like I said in the last one, when we want to receive bitcoins, we give away this hashed version of the public key. But if we actually look at all this data, so let's say this is a private key, and then this is a public key, which is a big number as well. These are typically stored in hexadecimal format. So let me just convert those quickly. And so when we hash all this data through those two hash functions, we end up with this hexadecimal number here for that hashed version of the public key. This works, and we can give this away to other people. That's fine. If you wanted to make it simple, you could just give people this direct hashed version of the public key, and that's fine. But the problem is it's not particularly user-friendly because, say you give it away or you describe this public key over the phone, say someone else types it in and they make a mistake and then they fill it out. If they make one single mistake, then it's going to send the bitcoins to a completely different address. So it's going to lose those bitcoins and this person's not going to receive them. So that's not good. So there's no error checking. So when you type in this hashed version of the public key, there's no way to check it for errors. Secondly, it's a bit long. So if you make it shorter, that would be great. But most importantly, there's no error checking. So what can we do to make these, basically the address is just going to be a more user-friendly version of this public key that contains error checking and is a bit shorter. So how do we fix this error checking problem? Well, what we do is we create what's called a checksum. So we hash this hashed version of the public key, and that will give us a long number. If we just take the first 4 bytes of that, the hash of this public key, that is called the checksum. And so we stick that on the end. And so what that means is, if someone was to type in this whole entire public key into their wallet software, if they make one mistake here, the wallet software can hash this and check to make sure that this part of the key matches the checksum. And if it doesn't, then they'll know someone's made a mistake somewhere. It won't be able to tell you where it's made the mistake, but it will say, wait there, you've made a mistake here somewhere, which is better than nothing. Similarly, like I said, it's a bit long. Can we make this any shorter? No. Now we've got the checksum here. It's made the public key a bit longer again. Can we shorten it down? Well, yes, we can. This version here has been encoded in hexadecimal format, which has 16 characters to choose from. What if this is just a number? Instead of encoding it in a format that uses 16 characters, what if we just use a lot more characters? So this is 16 characters here. What if you use the entire alphanumeric alphabet, which has 62 characters? If we can start using these, then we can represent this number in a much shorter space with a lot less characters. The problem with using all of these characters is some of them are a bit awkward to type out. Like zeros and O's look the same, so we don't want to use those. Similarly, an L and a big I can look the same, so we don't want to use those either. So if we just kick those out, we're left with 58 characters to choose from. So when you're encoding numbers in a particular format, the number of characters you have to choose from is also known as the base. So this is base 16 and this is base 58. Base 58 is just the alphanumeric alphabet or characters with the awkward ones taken out. So what you do, if you just take all this data, this public key with a checksum at the end, and you encode it in this format using base 58 characters, you get something a little bit shorter and slightly more user-friendly. But most importantly, it has this error checking capability, and that's why you'll often see addresses in this particular format. Hopefully this looks a little familiar. So basically it's just base 58. And this is what we call the address. So the address is just the pretty version of this hashed public key. There we are. So instead of giving the hashed version away, we could give the hashed version away if we wanted to. That's perfectly fine. But with wallets these days, everyone asks for an address. So you give the address away, and that means if they type it in and they type it in wrong, the wallet software can say, wait there, something's not right. So it's more user friendly to use this address, or safer to do so. Just to clarify, you can easily go backwards and forwards, encoding in base 58. This isn't using any particular hash function. All it's doing is just converting from one number format to another. Like converting from decimal to hexadecimal. That's one number conversion, but they're still the same number. They're still the same number ultimately. and you can go back and forth. Between hexadecimal, base 16, and base 58, you can go back and forth again. So what that means is when you do actually give a address or type one into a wallet, what the wallet does when it creates a transaction, it just works out what the hashed public key is, and then it'll put that as the lock. So even though you input an address, the wallet will convert it to this hashed version. So if you look at the blockchain, there aren't any actual addresses on the blockchain, in the locks at least. It's just the hashed version of the public keys on the blockchain or inside the transaction data. So does that make sense? Okay, great. Lastly, some coding examples. So if all this makes sense, you understand how keys and addresses work. So you have the basic private key and public key, which is the basics needed for sending and receiving transactions. Then you create digital signatures so that we can prove that we own a public key, that a private key is we can prove that we created the public key from a private key without actually ever having to give away the private key. And that's how the transaction system works, creating digital signatures. Finally, we made an address.
Yeah.
Gone. Okay. Yep.
Yeah, quick question. So addresses are actually just used for convenience, right? All transaction data have public keys and hash of public keys.
Yes.
Is that right?
The address is just like sort of the user-friendly top layer, but inside actual transactions, all they use is the public key and the hashed public key. The address is just for user-friendly purposes. So if you understand all that, then you understand how keys and addresses work. In this final part now, just run through quite quickly, not too complex, just how you can generate your own set of keys and addresses. I think this is quite fun to do. It's not terribly hard, it takes some coding, but you can actually easily create your own set of keys so you can send and receive Bitcoins. And it's quite a fun thing to do if you want to get started working with Bitcoin. So I'll just show you now all the technical stuff, how to actually create your own set of keys, starting with a private key. So let me just move this across, make that a bit bigger. So first of all, let's say you're doing some programming and you want to create your own generate your own set of keys. You first of all start by generating a private key. And if you remember, a private key is just a random number. The most important thing with generating this random number is that you use a secure source of randomness. This is the most important part by far. Make sure it's secure. Don't just use the standard random number generators in your programming language. They're probably not secure enough for this kind of stuff. So good sources of randomness, as far as I'm aware, is using the OpenSSL library. Every programming language should have access to it. Or if you're on Linux, use dev read bytes from dev urandom. That should be random enough for you. Alternatively, if you just have a Google around for your programming language, there should be a library that gives you quick and easy access to these two things if they're available. So in Ruby, it's called Secure Random. I'm not sure it is in other languages, but just have a look around for the most secure source of randomness in your programming language. It's very important. So again, so you've got a secure source of randomness. You need to generate a 256-bit number. So that's between 1 and a number that is 2 to the power of 256, which in decimal is this. But to be precise, it's actually the range of valid private keys is slightly less than this, and that's because of the limitations of the particular curve used in Bitcoin. In this curve, it has a parameter called n, which is just the number of points on the curve, and you cannot exceed this for your private key, and it's only actually a little bit smaller than 2 to the power of 256. It's very close to it, but just to be sure, I don't know if you can see this number changing, but this is 2 to the power of 256, but this is the n, or the number of points on the curve. So make sure it's below this. And if you Google around the name of the curve, SECP256K1, you can find the parameter for n. So there we are. We just generate a random number, making sure it's below this maximum value here. So that's the private key done. Just generate a random number. Secondly, now we want to create the public key. We need to use the elliptic curve, this one. And actually we need to do elliptic curve multiplication. But actually in your programming language, there probably is a library that gives you access to elliptic curve stuff. So you can just include that in and just ask it to do some elliptic curve multiplication. So you don't have to code any of this for yourself. You can just get a library in and it should do it for you. So what you do is you just do elliptic curve multiplication, multiply this generator point by this value, and that'll bounce on the curve, and the final resting point will be this public key. And the public key is the x and y value of this point. Obviously this public key is quite large. We've got two 256-bit numbers here, so that's going to take up a lot of space, and ideally in Bitcoin, because the blockchain is a shared file, we don't want to be taking up too much space if we don't have to. So what we can do, we can actually shrink this number down a little bit. And we can do that because one of the handy properties of this elliptic curve is that it's symmetrical along the x-axis. So what that means is if you have an x value, then the y value is only going to be one of two different values. So for every x value, there's only two given y values. So you can think of that as being y or minus y. One of the handy properties of this elliptic curve is that if this y value is even, then it means it's one point on the curve, say this one, or if it's odd, it means it's the other point on the curve. So when we want to store this public key, we don't have to store the full y value. All we need to know is whether it's even or odd. So this y value here is even, so all we need to know to store this full public key is that it's even, and then we can figure out what it was from there based on the x value. So this is the x value, and then we can just put whether the y is even or odd at the front. Obviously we don't put the word even at the front or odd. There are two codes for that. So if it's even, we put 02 like so, or if it's odd, 03. Early on in Bitcoin, public keys were actually stored using both the x and y value, and these are called uncompressed keys. So this is a compressed key because we don't use the full y value because we don't need to. But this wasn't known by Satoshi at the start that you could compress them. So a lot of early public keys use the uncompressed format, and if you want to use an uncompressed format, that'll start with 04, sorry. But this one's 02. So there we go. That is the public key. You just need the x coordinate and whether the y is even or odd encoded as a 02 or 03. Let me just convert all this to hexadecimal. I've been showing this in numbers just to illustrate that this is all just numbers, but when you come to look at private keys and public keys or pass them around, they're usually stored in hexadecimal format. So there we go. Now the private key is 32 bytes, and this public key should be 32 bytes also. Quick tip, if this public key is quite a low number, and when you convert it into hexadecimal, if it's not 32 bytes in length, make sure to pad it out at the start with the zeros to make sure the whole x value part of the public key is 32 bytes altogether. So just a quick tip. Otherwise, you'll end up creating an incorrect address later on. So okay, that's the basics done. Private key, random number. Public key, just do elliptic curve multiplication and store the y value in a compressed format. We just need to know if it's even or odd. Now we've got that, we just put that through two hash functions, because now we want the hash 160 of this to give away to other people. So we just put it through SHA-256 first, then ripemd 160, and that'll give you this digest, this result. Don't forget when you're hashing in Bitcoin to convert this to binary first before you put it into the hash function, and that'll spit out a binary result. Put that binary result into the next one, that'll spit out binary, then convert it to hexadecimal, and that gives you this hash 160 here. you might notice that this result, this digest, is a bit smaller than these 32-byte public keys. That's because SHA-256 is 256 bits, produces 256-bit results, which is 32 bytes, but RIPE-MD 160 produces smaller results, 160-bit digests, which is 20 bytes. So that's why it's a bit smaller, like so. Fine, okay, so this is what we give away to other people. This is the protected public key, if you will. But now we want to create the address, which is like a prettier version with some error checking involved. So what we do, we need to base 58 this. But before we do that, we first of all put a version byte at the start, which for most addresses is 00. I'll explain why we do that in just a moment. And then, like I said earlier, we need a checksum. So we just hash all of this, so the public key with a version byte at the start, hash it all to give us the checksum, hash it twice, like in mining. Then we take the first 4 bytes, that's the checksum, that's all we need really to be sure enough that this hashes correctly for the error checking. And then we put all that then through base 58. So public key, well, the hash version of it, version byte at the start, checksum at the end, stick it all through base 58. And that will give us this address. The reason we prepend this version byte at the start is because it affects the leading character of the address after we've encoded it in base 58 format. So for normal addresses where we just want to send and receive bitcoins, like in a typical way, we put 00 at the start, and that gives us a 1 address. So that means that we just want to send and receive bitcoins in a typical way. So if by changing this version byte at the start, it changes the starting character of the address. So 00 is for typical sending and receiving addresses on the mainnet network, but for testnet, so if you're on a testnet network, you put 6F at the start, and that will change the leading character. So there are quite a few of these different version bytes at the start to give you different addresses, but for most cases you're just going to use 00 to give you a 1 address. Yes, so I think I'll cover this a bit more in the locking code or script video, which will be coming up after this one. But for most addresses, you just want to stick 00 at the start. So there we go. That's how you can create your own set of keys just through this process here. Hopefully it all made some sense, or it's cleared up some issues. So there we go. Any questions about that? Okay.
Actually, just a quick question. You mentioned something about 32 bytes, right? Padding or something of that sort. For the SHA-256. Again, quickly.
Okay. I probably didn't need to mention that, but when you private keys and public keys, well, this X coordinate is always 32 bytes. Private key is always 32 bytes as well. Just a little tip that when you do this elliptic curve multiplication, say you get a small number for X, and then you convert it to hexadecimal, then you might end up getting a hexadecimal number that isn't 32 bytes long. If that's the case, just be sure to pad it out with zeros at the start, so that the X coordinate is the right length. Because that's important, because if you missed out a character here when there should have been a 0 there, then this is going to hash out to a different value. So you'll be sending bitcoins to the wrong place. So it's just I've made this mistake before, so I just wanted to bring it up to make sure that no one else makes the same mistake. So there we go. And that's how to create your own addresses and private keys and whatnot. So that's that part. Where am I to now? Here we go. So I've made a little script here. It's written in Ruby that will create a set of keys. Tries to go through in order. It starts off by generating a private key, just getting a secure random number. The maximum is this value here, which is n, like I said earlier, which is the number of points on the curve. So if that's too big, I'll just raise an error. So that generates a private key. After that, you need to go from the private to the public. So you just use the elliptic curve. You do elliptic curve multiplication, and then that'll give you an x and y value. So in the old format, it's just the x and y, but in the new format, if you want to compress the public key, you just take whether y is even or odd, and then put an O2 or an O3 at the start based on that. After the public key, you want to get the hash 160. It's quite simple. Just put it through two different hashing functions. So SHA-256 and then ripemd160. And then to get the address, you stick a prefix at the start, create a checksum by hashing the hash 160, and then the address is just all of that encoded in base 58. So here are some utility functions like the base 58 and stuff. And there we are. So here's the code. If you just run Ruby key generator, I'll put this code on the website or a link in the description. And this will give you a set of keys. And as you can see, it's quite fast. So even though we did all this, crazy elliptic curve multiplication, when you run the code, it's pretty fast to give you, your set of keys. So just to prove to you, here's an address. I can send some bitcoins to this address. There we are. Let's send a base description. Sorry. Test.
Is this
this is mainnet, just to show.
Okay. Sure.
There we are. Send a low fee. Send. Okay, so the payment's been sent. So copy that. Oops, sorry. There we are. Browser. Send the transaction. Look in the transaction. Right, there it is. So 1D9. That's the address I sent it to. So, like I said earlier, remember how the Electrum wallet took care of my change for me, and it sent it to a different address, like here, so the public key is protected. Okay, a few quick tips just before I go. This is a very good graphical address generator that shows you all the steps you need to do to generate your own addresses. If you go on the Royal Fork blog, Google that, and go onto the graphical address generator. It's very good. So if you're programming and you want to create your own set of keys and addresses, this is very, very helpful. It's helped me a lot. It's very good. Secondly, remember I said about you got all those different curves. The SEC P256K1. Well, they're all outlined on the SEC website. So here's I'll put a link in the description. Here's the here you are. So here's the parameters for that curve. So you have lots of different curves, but this is just the one that Bitcoin uses. That one. So, yep, there we go. One last thing before I forget. For these private keys, you also have what's like an address version, like a pretty version of the private key, which is called wallet import format. I haven't covered it here, but it's very similar to this process for getting a pretty version of the public key. So if you ever see wallet import format, it's just the pretty version of the private key. Any questions?
Oh, that's awesome.
No problem.
Thanks,
I'm glad it all made sense. I tried to make it as flowing as possible, because it's quite a lot, I thought, with the elliptic curves and stuff, to include that in and cover how that all works. But I just wanted to cover the basics of keys, really.
Sure. Yeah, and one time is not enough. I'll have to review the video.
Yeah. No, I felt like that. I felt that as well. When I was doing the video, I was like, oh god, this is quite a lot of information. It's hard to it's hard to take in all in one sitting. But
Right.
maybe if you want to learn, go
Yeah,
on.
and yeah, end of the day, it's just like transformations, right?
Yeah,
I mean,
it's just numbers. I think if you just went through this
yeah,
process of creating your own set of keys, I think you'd learn everything as you went along. But hopefully this gives you a primer
exactly.
to get going, I suppose, and create them.